Hello guys, today I'll be talking about the moment of inertia, and rather than going for the formulas which are already available in the book, I'll talk about the physical significance of it. So moment of inertia can be classified basically in two ways. First is the mass moment of inertia, second is the area moment of inertia. Now inertia can be interpreted as resistance. So when we talk about the mass moment of inertia, it can be said as a resistance to rotation, and when you talk about the area moment of inertia, we can say it as a resistance to deformation. Okay. Now the mass moment of inertia depends upon the mass distribution from the neutral axis, because since we are talking about a rotation, so there is a neutral axis over which the mass is distributed. So what we actually do is we divide the object into small fragments of mass dm. Dm is a very small fragment, and we integrate up to the contribution of r square dm, where r is the distance of that particular small dm from that the area of the axis of rotation. Okay. So the objects which are having the mass distributed away from the axis will be having the more mass moment of inertia, and vice versa, the objects with the mass distributed near to the axis will have less mass moment of inertia. Okay. So you can say that if the body is having a high mass moment of inertia, it has more resistance for rotation. That means more torque is required to attain a given acceleration. If you want to make it roll, you have to provide more torque if for a body which is having a more mass moment of inertia. All right. So generally this mass moment of inertia concept is used for the design of rotating systems such as flywheel or gears. Okay. Now when we talk about the area moment of inertia, it tells us basically about how the cross-sectional area is distributed upon a particular axis. Okay. So you can simply understand it as a resistance to the bending. So, okay. So in this figure, if you see below, you have two axes. One is xx, one is a yy. So you can calculate the moment of inertia uh, with reference to axis xx, also with reference to axis yy. All right. So the axis which is having the more moment of inertia will have more resistance for bending. Okay. The axis which is having less moment of inertia, I'm talking about the area moment of inertia, will be having less resistance for rotation, and that axis will be considered for design calculations. All right. uh, let's go for a hypothetical situation where we are trying to roll two cylinders. Okay, one is a hollow one. The one in the top you are seeing is a hollow one. The one in the bottom you are seeing in the is a solid one. Okay, so given everything is same, which one do you think should win the race if we leave them at the same time? Okay, think about it. uh, it is actually counterintuitive, but actually the cylinder with the solid cross section will win the race. All right. So I'll just try to tell you how it happens. So when the cylinders, both the cylinders are at the top, it is having some amount of potential energy. All right. Now this potential energy will go for two purposes. One is a translation kinetic energy, that is that will travel it from this point to this point. Okay. And the other one is a rotational kinetic energy, which will allow it to roll while it is moving. We are considering that there is no slip involved. Okay. So I just have written the formula of it. Basically it's a mgh is equal to half of mv square, which is a translational kinetic energy, and half of I omega square, which is rotational kinetic energy. All right. So for hollow cylinder, what happens is moment of inertia is more. Why? Because the mass is distributed away from center. As I told before, if the mass is distributed away from center, the moment of inertia will be more. Okay. That means it has more resistance for the rotation. Now since it has more resistance for rotation, it will need more energy to overcome the rotational resistance. Okay. Now this is the point that you have to understand. So given both the solid cylinders and hollow cylinder initially have same mgh, the hollow one is taking more energy to overcome the rotational resistance. All right. So less energy is available for the translation kinetic energy. Understand? So if less energy is available for translation, it becomes slow. Okay. For the solid cylinder case, the moment of inertia is less, as the mass distribution from center to end is less. Hence, it has less rotational resistance. Hence, it becomes the faster. So the only thing you have to worry about is if there is a body which is having more moment of inertia, it will use more energy towards the rotational towards rotation because it has higher rotational resistance and less will be available for translation. That's why the solid cylinder will be winning the race. All right. So this is a typical example of mass moment of inertia. Now, when we go for a area moment of inertia, I would like to you to take back at a time where when we have studied strength of materials. In that, there is a formula for a columns and struts, the critical load for column and strut. That critical load is the maximum load allowable for a column to withstand. Okay. Now that critical load formula is pi square EI upon LE, where pi is a pi, E is a Young's modulus, I is a moment of inertia towards a cross section, and LE is the effective length that changes depending upon what kind of the end scenario is. It's a either both ends fixed, both end hinge, one fixed, one hinge, or one end fixed, one end is free, like that. Okay, but I don't think this is the correct formula. The correct formula is basically P critical is equal to pi square E I min. Now you have to focus on the this I min thing. Reason being, this I min is a crux of this formula. Okay, why do we have to go for the I min? Okay, I would like to explain that. So just assume you have a cross section of this column in such a way that you have two axes x and y. Okay, let's assume for now that height for the height is 10 of any unit and breadth is 20. Okay, let's assume it's or only. Okay, now if we start calculating the moment of inertia towards x and y, you will go for with the formula bh cube by 12 or hp cube by 12 depending upon which axis you are choosing. I hope you are aware of it. Since h is less than b, hence ixx will be less than iyy. Hence, moment of inertia for, from the axis xx will be lesser than the axis yy. All right. Hence, that means it has less resistance for bending towards ixx. Now you have to understand this point. The axis ixx is having less moment of inertia, hence it has less resistance for deformation. Hence, the more failure chances are from the axis xx. Hence, it becomes critical for the design. All right. So whenever you design a column or a straight, you only take care of the axis which is having less moment of inertia. All right. I hope you understand right now what is the difference between the mass moment of inertia and area moment of inertia. All right.